and welcome to my channel. Today we're going to have a look at the circuit I found which I thought was interesting and a little dangerous again. Let's just have a quick look at the video first. So that's the schematic. Looks pretty straightforward. Let's go into it a bit deeper. Starting with this little friend here. The first thing that's really obvious to me is the fact that this is a pretty simple circuit. I'll just clean up my previous bit of work here. So what we've got here is we've got the diodes, each is a different colour. First thing to note over here, the forward voltage, which is a very key thing, and he hasn't really taken into account how the voltages here work. So what we need to look at here is 47K, 220 mics diode. Now, absolute first thing stands out to me right here. No safety concerns, no fuses, no filters, nothing. Secondary thing to note, if the electricity is supposed to flow this way through the circuit, that's in back to front. Yep. So we've got a duff gen already. The first problem is that the circuit has its problems, so the diode's our first issue. Got a highlighter mark on that. Know where our first mistake is. Now, next thing we want to look at is how on earth do you work out what this circuit's going to do? Okay, a couple of things to look at. All those combined, I did a very quick calculation and I made the assumption that we were somewhere around 80, but also went right down the bottom of 5 milliamps. And just a quick dirty way to check the circuit, ignore those for the moment and just simply work out the current as a function of the resistor, nothing else. So the current that will flow will equal, and this is an approximation only, 220 volts divided by, helps if you draw properly, doesn't it? And 47K. Now, I did a quick calculation earlier on. This comes out at approximately 4.6 milliamps. As soon as you do that, then there's this whole new thing that pops up. You have to look at the fact that if that's 20 milliamps, and that's about 4.6, about 5 milliamps through here, what we're going to see is this more or less line. I can't draw a straight line with this thing yet. I'll get there. I was told with straight edge usually helps you do this kind of thing. Now, where are we? Point is a little hard to spot sometimes. Use a pen. In any case, got into this and I've had a look at it, and the forward voltage is actually about 11. The sum of the forward voltages, when you work it out, around about the 5 milliamp mark. You're going to get around about 12 volts as the approximate value that you'd be looking for out of that. Let's come back to this colour, make this a bit easier for ourselves. That's a terrible colour. A couple of things to consider. Halfway rectifier, let's assume it's around the right way. would give you, I'm making a horseshoe. Now that looks like an ohm symbol, doesn't it? We'll try that just once more. When you think about using a tool like this, it takes a little bit to get used to. Alright, straight line, and then we have the half cycle, and then we get a half cycle again. So we only pump electricity for a portion of this. The 47k resistor restricting down to 4.6 milliamps would enable you to build some voltage up in this, but there's another thing to consider. We also need to take into account the time constant. So we've got two things to consider. One is, what charge, Q, does that capacitor get on it? And you can't answer that question properly because this is not DC, this is dynamic, and you actually need to use time constant is equal to the resistance R multiplied by capacitance, and it's in seconds. Now if we take this one here, R's 47k again, multiplied by 2.2, oh it's terrible this one, E minus 4, 1, 2, 3, 4. For those two, and our time constant comes out around about 2.2 times 4.7, it's nearly 10 seconds. Now, the significance of 10 seconds, so a very quick look at the graph here. If you were looking at the time constants and the charge cycle, TC equals RC, and that is one time constant. Then you get 2, 3, 4, 5. Let's pretend this is going up to 1 volt. That's just for illustration so you can get the idea. In one time constant, you will reach a value of approximately 63% of 1. Two time constants, you're going to love this one, is 63% of the remaining 37%. It's up there. Now we go for the third time constant, a bit less, and a little bit less, and for most practical purposes in circuits that you work with on a day-to-day basis, you get this curve that looks like this. And I can't draw very straight, but basically it's 1 minus natural logarithm e to the power of t. That's it. As t grows in size, this thing just goes up and up and up. Now let me see if I can get my lines to be a little bit neater on here. It's definitely easy to draw this by hand, isn't it? Okay, I need to spend a bit of time practicing with this because this is just so difficult. Alright, here we go. Let's see. I need to actually put my hand on the inside of the curve first. So here we go, it comes up and starts to come around. Around. It's a bit better. So we have to account for this 63% of whatever voltage it's just trying to generate. We'll assume that's got almost 0 ohms to start with, and it'll be 63% of about 12 volts, what it's going to try to aim for. So now let's change the figures out to match approximately 12 volts that it should be aiming for, and the fact that this has a 10-second cycle and this thing is pumping at a rate that is not 10 seconds. We've got 50 hertz, 20 milliseconds, so each cycle is about 10 milliseconds. An approximate square wave would look something like this. Let me pick a nice new colour for this one. An approximate square wave that would be used here would look something like this. It'd simply go something like this. Yahoo! And you can see this is getting down to probably about 6 milliseconds per pulse. So these are like little pulses, this is supposed to be 220 going through that onto that. And what we would get if we looked at the voltage of our device is that the voltage would get a bump and sit relative flat and get another bump, sit flat and get another bump and get flat. It just does this until it reaches the LED threshold. So the sum of V4, which is about 12 volts, at which point the capacitor will discharge. Sorry, it doesn't equal 12 volts, it's actually right down here. And it's still around about 8 volts. So when it hits 8 volts, the capacitor will discharge until no more current flows, and then it will start bumping up again. And it'll give a flash and come down. I think that's where a lot of people kind of miss the point what these things are doing, because they actually do this continuously. So this one's not impossible to work out, but it's definitely not easy to work out. Right. Now a couple of things to look at, because that's in back to front. It will pull power this way, probably overpower those, because they're at a high impedance, which means this won't have much current drop once that charges up. And all of a sudden these are just one or more of those are going to let go, and kabang, they're gone. People do make mistakes with this stuff. You can get yourself electrocuted. I'm a big believer in putting something in here, including proper earthing, because without proper earthing you're going to hurt yourself. That is really, really important. No earthing, no safety. Alright, I think I've been through that enough. I think we'll kind of get the idea. And again, as I said in one of my early electronics ones, what's the category this is safe to use it in? I'd suspect that this is not really safe in any category. In any case, I really appreciate what everyone's done, and I appreciate people watching. It's always a pleasure to talk to an audience, whether you're actually watching or not. Bye for now. Please remember, if you like what you're seeing, let me know. If there's anything wrong, put the comments below. I will have a look at those. I certainly do respond to people that say something like, "It sounds buggered," because that's not fair on them. They came to my channel, I messed up, I have to fix it.